Now we're going to talk about mixtures of gases. Now, the reason we're going to talk about this is because actually most gases are mixtures. If you're trying to just like contain one type of gas, you'd have to do it in the lab, right? There's all kinds of stuff in the air. So we do have to take that into account. There's mixtures of things in gases. So probably the easiest law of all of the gas laws is Dalton's law of partial pressure. And that is that gases don't affect each other when they are mixed. Now, they don't really interact, they spread out themselves, and that's about it. So it means that since they don't interact with each other, unless it was a chemical reaction first, pressure, like the moles, is additive if I put them together. So this visual will hopefully see what I'm talking about. So if I had 0.6 moles of hydrogen gas, it takes up 2.9 atmospheres. That's the pressure for that many moles, okay? Now, if I have the same size container at the same temperature, and I have 1.5 moles of helium in it, the pressure is 7.2. If I put them into the same container at the same size, I can just add the pressures together to get the total pressure. Again, if everything else stays the same. Okay, same thing happens with the moles. I'm just adding the moles together. The pressure is just additive. So its equation looks like this. The pressure total equals what's called, these are partial pressures. So the pressures of each gas, P1 plus P2 plus P3 plus however many gases are in your mixture. So anytime you have a mixture of gases, you are probably going to have to be using Dalton's law. Okay, so I'm going to do example number 14 with you. Okay, so I have a 1 liter vessel, and I'm going to pull all these numbers out. So I have a volume of 1 liter, contains 2.15 moles of N2 gas. So N is moles, right? That's 0.215 moles. That's specifically for N2. And 0.0118 moles of H2 gas at 25.5 degrees Celsius. So what is that temperature wise? There we go. It is 298.65 Kelvin. Okay. I have pulled out all of my numbers. So I have a volume, I have 2 moles, and I have a temperature. So if I'm putting them in the same container, right, a 1 liter vessel, what I want to do is determine the partial pressures of each component and the total pressure. So if I find the partial pressure of N2 and the partial pressure of H2, I can add them together to get my total pressure. So anytime you just have a mixture, notice there's no chemical reaction happening here. I'm just mixing them. You can add those pressures together. So I'm going to have to do them each separately, right? I'm going to do N2s and I'm going to do H2s, and then I'm going to add them together. So I need to find the pressure of N2. All right, so for N2, I'm going to use its numbers. So the pressure of N2, that's how I'm going to denote that. That's how you would write like the partial pressure of N2 times the volume. Now they're both in the same container, so they're both in a 1 liter container. They both have the same volume. Equals N is 0.215 moles, R 0.08206, and temperature 298.65. Okay, so I can very easily find the pressure of the nitrogen using Pivner. That's all I did. So that is 5.27 atmospheres. Do the exact same thing for hydrogen. pH2 times 1 equals, the only thing different is the number of moles of hydrogen, because they are in the same container, same temperature. Okay, so pH2 ends up being 0.289 atmospheres. And then, so I wanted to find each of the partial pressures and the total. So the P total would just be them added together. 5.27 plus 0.289. If I do my sig fig rules, I get 5.56 atmospheres. And that's it. So anytime you have a mixture of gases, all of the same rules apply, but we just added in Dalton's law of partial pressures. Okay, so this brings us to mole fractions. And that's just like the relative amount of gas in a mixture. So like how much of it was nitrogen, how much of it was hydrogen, moles wise. So the way to find mole fraction is very easy. We do represent it with a capital X, and then down here would be like whichever one you're talking about, you would write H2 or N2 or whatever. So mole fraction is equal to the moles of that one gas over the total number of moles. Really easy calculation, right? And that is on your equation sheet. The mole fraction is equal to the partial pressure fraction. So like you put the partial pressure of one gas over the pressure of total, it's like a ratio. It gives you the exact same value. So if you know the mole fraction, you can find like a partial pressure from if you know the total pressure. So we can kind of use these equations to figure out how much of a mixture is one specific type of gas. Okay, so example number 15 says, what are the partial pressures of both N2 and O2? So I'm looking for PN2 and PO2. If there are 28 grams of nitrogen and 16 grams of oxygen, so I have grams of both, go ahead and convert those to moles. You know, if you have grams, we don't put grams in any of our calculations for gases, so go ahead and convert it to moles. Present at a total pressure of 900 millimeters of mercury. So pull out your numbers first, right? I told you got grams of this, go ahead and convert them to moles. So this is 1 mole of nitrogen and a half a mole of oxygen. I want to know what the partial pressures are. Well, all I gave you was the total pressure and then how many moles of each. So the best approach to this would be to find the mole fraction, which is the same for your like pressure fraction. So I have 1.5 moles total. So my nitrogen fraction is 1 over 1.5, which is 2/3. And my oxygen is 0.5 over 1.5, which is 1/3. So 2/3 of this mixture is nitrogen and 1/3 is oxygen. Okay, so the same holds true for the pressure. So this is my mole fraction here is equal to the partial pressure of nitrogen over the total pressure, because remember, that's all I gave you. So I plug that in down here. I solve for my partial pressures. I get that the partial pressure of nitrogen, right, it's 2/3 of the sample would be 600, and the partial pressure of oxygen would be 300. And you can see my mole fraction calculations down here. Now, seldom do I ask for just a mole fraction, so you're going to have to like use them in this context. But you can use mole fractions with partial pressures to find like how many moles of gas there are in something, or how many grams of gas. You can find moles and then convert to grams, or the other way, like we just did with finding pressures. Okay. Example number 16, we've got a 1 liter sample of dry air. Dry air would be like what's in the air, right? So definitely a mixture of gases at 25 degrees Celsius and 786 millimeters mercury contained. This is a lot of numbers. So I'm going to pull these out and break it down. I'm going to do this with you. Okay, so 1 liter of a dry air sample, which is like nitrogen and oxygen and carbon dioxide and all that stuff. So I've got a volume of 1 liters at 25 degrees Celsius. So what is that? 298.15 Kelvin. I have a 786 millimeters of mercury. So that's going to be my total pressure. So P total is 786 millimeters of mercury. I don't know if I need to convert that yet. We'll check and see what equations we're using. And I have this much nitrogen. What is the mole fraction of nitrogen? So, well, I've got grams of nitrogen. Let's just go ahead and convert that to moles, because I know I'm going to have to at some point. N2 over 1, N2 is 28 grams. All right, so what do I get here? This is 0.03304 moles of N2. Awesome. Okay, so I have an N here, and N2, not the whole thing, just the nitrogen part, is 0.03304 moles. Okay, so my one issue here is that this looks like it's going to be a Pivnert problem, except this is the total pressure, but this is not the total moles. So I can't like plug them into the same equation. Now I am going to use Pivnert, but we kind of got to take a different approach then. So if I know how much is nitrogen, right, and I know my total pressure, maybe I can find my total moles, okay? Or you could find your total pressure. Either way, I'm going to use Pivnert, PV equals nRT. I have a V, I have a T, and then I can use either this one or this one to find what I'm looking for. Okay, so I think what I'm going to do is I'm going to use my total pressure to find my total moles, because it says what is the mole fraction. So I need the total moles, because I'm going to put the moles of N over the total moles to figure it out. So let's plug these in. So I am going to convert this. 760 is, what is that pressure? Did I write it down? I don't think so. Hang on. Okay, so that total pressure is 1.0342. So 1.0342, that's my total pressure, times 1.00, that's my total volume, equals, I don't know how many moles total, Okay, again, you have to keep it specified as to what's total and what's like a specific element. So that's what I'm going to write total there. 0.08206 and 298.15 Kelvin. Okay, so this will tell me how many moles of gas total are in there. All right, it doesn't actually matter what kind of gas it is. They all behave the same way. So that divided by that and that, I get that the total moles is 0.04227. All right, so I'm looking for mole fraction. This is my symbol for mole fraction. I want the mole fraction of N2. So I put the N part, N2 part, over the 0.04227 part, which is the whole thing. And that will give me my mole fraction. Now it should always be less than 1 because total is going to be 1. So 0.03304 divided by the answer, I get 0.781. And it is a fraction, it's not going to have units. So that is the mole fraction for nitrogen. And you could have approached this a different way. You didn't have to do it exactly like me, but you would have ended up using the same equations. This really comes into play is in the lab. So collecting gases is a little bit more difficult when you're doing some chemical reactions, and you're going to do this in lab as well. And one way that we kind of combat this to collect a gas is doing what's called collecting gas over water. So anytime in a problem or in lab, when you collect gas over water, you're going to have to take into account that, say I'm doing this reaction over here, okay, and I'm trying to collect that gas. So it goes through this tube, I bubble it through water, so that if I started with a vacuum in here, now the only thing in here is the gas I'm trying to get. The problem with bubbling it through water is that you also get some water vapor in here, some gaseous H2O, and we have to account for that. It's not pure gas, whatever it is that we're collecting. It also has some water in it. So at the end, so the way that we do this, we gather it in here. Okay. And it's really hard to like stick a pressure sensor in there, right? So what we do is if you move this container, which is usually like a giant beaker or something, up and down until you get the water levels the same. If the water level on the inside and the outside are the same, then that means that the pressure on the inside and the outside are the same. So if we know the atmospheric pressure, which is very easy to find, we know that that is actually the same pressure in here. So the pressure inside is equal to the outside. That's going to help us with our calculations and figuring out like how much gas did we make. So anytime you collect gas over water, you're going to have to use Dalton's law of partial pressures. That after I equilibrate it, that the pressure of the atmosphere, so the outside, is equal to the inside, which is the pressure of your gas, but also there's some water. Now, how much water? You're actually going to look that up. So then you can like subtract and figure out how much is just your gas. So you would be given this table. So like at different temperatures, there are different pressures of water. They're called vapor pressure of water. So say I did this experiment at 15 degrees Celsius and I collected gas. Well, how much of that gas is water? At 15 degrees Celsius, it's 12.8 torr or 12.8 millimeters of mercury. Whatever the rest is the gas that I collected. So you just have to take into account that there is some water there. Okay, so in here we have calculate the mass of O2 produced by the decomposition of KClO3. We used this equation earlier. When 821 milliliters of oxygen is collected over water at 30 degrees Celsius and 1.015 atmospheres. Now, first off, this looks like a stoichiometry question. Right? I've got oxygen in KClO3. I have the oxygen. What am I trying to find though? Okay, so I have milliliters of oxygen collected over water, and I want to know the mass of oxygen. Well, I don't actually care about the reaction part. I'm just trying to figure it out at the end. So we don't have to do stoichiometry here because what I'm looking for, the oxygen mass is the same as the thing that I collected. So yes, I did do a stoichiometry question, or I did do a stoichiometry problem. I did a chemical reaction, but I just care about the oxygen. KClO3 has nothing to do with this problem. So I don't have to do the stoichiometry problem. I do have to take into account that I collected it over water. So that pressure that I have, this 1.015 atmospheres, is the pressure of oxygen and water. So before I plug it in or try to calculate anything, I have to subtract out the water part. Okay, so anytime it says collected gas over water, that means my pressure is actually a partial pressure of water and the thing I collected, in this case, oxygen. So I'm at 30 degrees Celsius. So I look at my table and I'm like, okay, if the temperature is 30 degrees, then the partial pressure of water is 31.8 torr. I'd probably convert that to atmospheres because this one's in atmospheres and they need to match. So what I did first is I converted this to atmospheres. So the water part is 0.04184 atmospheres. The rest would be oxygen, and that's the thing that I talked about. So what I did is I used Dalton's law. I said, well, the total pressure was 1.015 atmospheres equals the pressure of oxygen, which is what I'm looking for, plus that pressure of water. So you're really just going to subtract it out. Now I have my pressure of oxygen. Now I can plug everything into Pivnert and get my moles for just oxygen. So that's what I did down here. And let's see, I got that many moles of oxygen. The question is asking for grams. So I just multiplied by the molar mass. So that must mean I collected 1.03 grams of oxygen. Okay. So make sure you read carefully. Collecting over water, you have to account for the water part.